So welcome back to a new week in Physics 321, and I'm glad you could attend via Zoom. This is going to be an exception, obviously, essentially due to a family emergency, as I wrote to you in the email. It means that today's lectures and Wednesday's lectures, we're going to run it in this modality here. On Friday, Tuju and Abby will be present in the classroom in the STEM building, whereas I will be present online and help people with the homework exercises from via Zoom. So let me just bring up the schedule for the day, and please don't hesitate to write questions in the chat. So if we look at the kind of plan which we have for this week, the aim is to start looking at other examples and how we can integrate the equations of motions. And we are going to move from 1 dimension to 2 dimensions. And as I said last week, I mean, this is when I get on shaky ground. I'm a classical 1-dimensional person. You will find recommended readings. This is the textbook by Taylor. And the examples which we're going to look at, they're actually taken from the sections 2.1 to 2.4. There's also the textbook of this colleague of mine, Malte Sørensen, on chapters 6 and 7. That is a textbook which contains a mix of numerical exercises and analytical solutions. And it can be of help when you're solving the different homeworks. And that textbook is something which you can download for free if you go on an IP number of Michigan State University, because it's a textbook published by Springer. And all those textbooks can actually be downloaded for free, and you can just get the PDF file. The plan for Wednesday is also to look at further examples on applications of forces, so that we get a little bit more reacquainted again with Newton's equations and how to solve them. And we're also going to look at some of the exercises from the second homework. And on Friday, we will continue with that. And depending on how far I get on Wednesday with the examples, we are going to dive into the new topic, which is actually the energy work theorem, which is something which will keep us busy parts of next week as well. Now, one small message which I also wanted to give you, and you've probably seen that on D2L. So if you go to the standard GitHub page of the course and you scroll down to the weekly schedule, you will see now that I've posted the solution to the first homework assignment. And if you click on this link here, we are going to fill that link with the different assignments. So we will normally publish these assignments, the solutions to them, the Monday after the deadline. So the deadline was on Friday, but you had still some possibility to submit by Sunday. And typically the Monday after the deadline, we are going to publish the solution to the homework. So gradually we will fill in under the schedule here the solutions of the different homeworks, and you will also find the link published under your D2L page for Physics 321. Any questions so far? Something which may be unclear, or things which you would like to ask about practicalities before we just move on to today's topic? So the topic today is now to look at the different equations of motions, and then how to solve them with and without friction or air resistance. So let's just move to the whiteboard immediately. So we will basically stay with the whiteboard for the rest of the day. And so let's bring that up here. So the simple case which we looked at last week was a case with just the gravitational constant. So we were looking at a falling object, and this is a type of problem which we can solve analytically. It was not the very most exciting case which we can look at. And in this particular case, what we decided upon is that the acceleration as a function of time is just given by a constant minus g, which is the gravitational acceleration. And then, since this is now pointing down in the y direction, we would multiply this with a unit vector of j. So if we look at the coordinate systems which we have chosen, if we go in 3 dimensions, we would typically have X, Y, and Z. But in this particular case, we've just limited ourselves to 1 dimension. And then the coordinate which we are looking at is just the Y direction, or if you prefer the Z direction, it could be that. This is up to you which kind of direction you would choose as the 1-dimensional unit, the system which we are operating with. So in this case, in the 3-dimensional case, we would have a unit vector in the X direction given by this label I, and then the same in the Y direction. And in the K direction, in the Z direction, we would have the unit vector K. But it's pretty common to label the axis for Y when we are looking at an object which is falling in 1 dimension. So now we are just falling down in the negative Y axis, in the direction of the negative Y axis. And then what we did, since we know that the force is given by Newton's law, and we are skipping now the time dependence, and this is the same as m times the second derivative, and just a quick reminder what we did last week, and r is now the position vector, and r is now given by the, if we are dealing with a Cartesian coordinate system, r is given by x in 3 dimensions, and then we have the y component multiplied with the unit vector in the y direction, plus the z component multiplied with the unit vector in the z direction. So that means that the acceleration in this specific case would also be given by a component in the x direction times y, and a component in the y direction times the unit vector, plus a component in the z direction times the unit vector in the z direction. This is just to set up the kind of notation which we're going to use. And when we are looking at the problem in just 1 dimension, there is obviously no need to introduce vectors because we just have scalars in 1 dimension. So in 1 dimension, what we have in our specific case is that F is now given by the gravitational force, and this is simply m times g. And we have the acceleration, which then is simply minus g here. And we are taking away the unit vector because there's no point in having it since we're just in 1 dimension. And in this particular case, the way we could solve this problem is simply to integrate. So we would rewrite the second order differential equation in terms of 2 first order differential equations. And we know that the velocity in this case is given by dy dt, since we have defined the direction in which this falling object is moving as a y direction. And then we have the acceleration, which is given in terms of dv dt. And the strategy which we went through last time was simply to integrate up. And what we got then is that the velocity at the time t minus the velocity at the time t0, which we indicated by v0 for the initial velocity, is something which we could simply integrate up as minus g from a t0 to final time t, and then we had a dt here. And we found then the famous equation, which many of you have seen before, of t minus t0. Now you may wonder, are we just going to stay with this simple equation for the acceleration? Now what we could do now is to actually add some kind of air resistance. And air resistance, or friction, as we discussed last week and the week before, is a force which acts against the movement of the object. But unfortunately, we do not have, and it's a contact force, we do not have a fundamental law for friction. And the expressions which we end up with then are expressions which are determined from phenomenology. Now, in the lecture slide, you will find a video to an explanation of how you could model the air resistance or the drag or the friction. So what we're going to do now is simply to add some air resistance, and we're going to stay in the y direction only. Air resistance in 1 direction. And this can be done with the 2 empirical formula, which are extracted from experiment. So we could now write this FD here F for the drag or air resistance. And we are going to deal with a one-dimensional quantity. So this is going to be given by something which has a constant multiplied with the velocity squared as a function of time. And I'm skipping the function of time dependence. It could be like that, or so if v is a large velocity, if v large, or whatever we define with large is something which depends on the experimental situation, or we could have something which goes like a new constant, and we're going to call this constant for a gamma multiplied with v. So we can have something which depends on the square velocity, or something which simply depends on the velocity. And this is typically a phenomenological formula if you have if v is small. Now, as I said, there is no kind of deep fundamental law which allows us to extract a nice analytical expression for the air resistance or friction at the same level or same footing as we have for gravitation. Now, if we look at this case, this is also one of these cases which we can integrate analytically. And you're going to study this specific case in homework number 3. So I mean, not this homework, but the next one. And in homework number 4, we're also going to add the possibility that an object which is falling down, when it hits the ground, can actually bounce back again. And then we can look at an object like a falling ball, which bounces up and down till it comes to rest. And depending on the way we model the contact force with with ground and air resistance and so on, this object will jump up and down in different ways. Okay, so if we now look at this specific equation we have, we can now go back to the total force, so what we call the net force. And this is going to be given by gravity plus this force F of d here. So that means that we are going to have something which looks like, and now we are going to set up the case with the square velocity dependence. So we're going to have a d times v squared. Now, the next thing which we're going to do now is to actually rewrite this equation. So that gives us an acceleration, a total acceleration, which is going to be given by F net. This is a total force acting on the object. And it's a little bit similar to what you're looking at in homework number 2, where we are looking at this person falling down and then unleashes the parachute and opens that up. So very similar arguments can be used when you're going to schematically discuss what happens with somebody who jumps with a parachute. So we can now divide this by m. So we are going to get something which goes like minus g plus this d divided by m times v squared. And now I'm simply going to relabel this constant d with and d divided by m with a d tilde with a v squared. So this d tilde is the original constant d divided by m. Now, the next thing which we will do then is that we know that this is equal to dv times dt. And this allows us now to rewrite everything. So if we now just proceed a little bit with this equation here, we can now try to integrate and see if we're able to do that. Now, what we will do now is first to divide by the quantities which we have on the right here. So we can isolate dv by multiplying with dt. So we would have minus g. And what you see now is a pretty common trick, which is used when we try to solve this type of equations. And if we look at what we have on the right-hand side, we have something which depends only on time. So we can now make an assumption here that we can integrate up the right-hand side without thinking of the velocity itself. This is a technique which is often called separation of variables. Now we are going to make our life a little bit simpler. So we're going to define initial time t0, which we just set equal to 0 time. And this is pretty common. And the next thing which I'm going to do now in this equation is to define another quantity, which I'm going to call for vt. So this is just a constant which allows me to get rid of other constants. And we are going to define that in terms of G divided by this quantity D tilde. Now, feel free to ask questions while I'm moving on here. This is perhaps not the most exciting exercise we're going to do, but it's going to serve an interesting purpose, because when we go to 2 dimensions, for one of the cases with the velocity, whether we have velocity squared or just simply the plane velocity dependence, we are not going to be able to find an analytical solution in 2 dimensions. And that is why in homework number 3, we're going to look at this problem from a numerical point of view in 2 dimensions, but we're also going to use the 1-dimensional case to test that our code is functioning correctly. So this will be your first encounter with both a 1-dimensional case with a falling object and the 2-dimensional case, which for one of these models for the air resistance can only be modeled by numerical efforts. So let's now look at the equations which we have, and we take the right-hand side. So the right-hand side is something which we now can integrate from t0 up to t. And then we have a dt prime. And this is just going to give us, with t0 equal to 0, it's just going to give us t. And then what we have next, and we are going to put in an initial condition, we're going to assume that v0, the initial velocity, is equal to 0. And then we have now an equation where we can integrate. So we can integrate with respect to velocity only. So we integrate from 0. But now we integrate to final velocity. And then we have a dv divided by minus g plus d times v squared, because here we have isolated the differential of dv with only d on the left-hand side. So we are simply now assuming that we can separate the variables, and we have a right-hand side which depends only on time here. Now with t0 equal to 0, this simply becomes equal to t. Now the equation which we have in the denominator here is something which we now can look up in mathematical formula. So this integral here, so you can look up table of integrals, and you will recognize this as something which is equal to the tan inverse, or arctan. Look up table of integrals. Alternatively, you can use symbolic Python, or you can just use Mathematica. Now, one thing which I would like to say is the following. So you can, if you wish to, you can solve these integrals by paper and pencil. This is actually a famous integral if you now reshuffle it, because you will have something which depends on the variable v, which we are going to integrate. So I should put a v prime here, by the way. I forgot to do that. You can then integrate this one because you have 1 divided by some constant plus the v prime squared. And this is something which has a nice analytical expression, and you can look it up in table of integrals. Alternatively, you can use Mathematica. So when you're solving homeworks or midterm exercises, or you're doing the final exam, we accept as ways to find the solution to an integral the standard paper and pencil solution. You can use symbolic Python, you can use Mathematica or other symbolic languages. So this is up to you, because in a certain sense, there is not much insight in solving these integrals by brute force paper and pencil. It's always a nice exercise to do it, so feel free to do that. I love solving integrals, but if you are short of time, I mean, it's always handy and useful to use something like symbolic Python or Mathematica if you have access to it. So I'm just going to give you the result here. And one thing which we are going to do now is to manipulate the variables, so I can get this term vt, which you see here, inside the integral. So let's take a look at this integral here. And what we are going to get then is that v of t, since we put v0 equal to 0, is then going to be equal to this constant vt, which we have defined, divided by g. And then this contains the inverse tan, h, tan hyperbolicus. And it has as an argument the velocity v. divided by v of t, and this is equal to minus t. So what I can do next now, since I have the inverse tan here, I can simply now just simply invert that one, and that gives me, sorry, this is not, I shouldn't, the integral here. So this specific integral is actually equal to that. And then I take the inverse of tan h inverse. So, and I multiply with vt and g and with minus t here. So this means that I'm going to get v of t, which we have in here. This is t with a v with a t dependence. And this is going to be given by v of t and multiplied with tan h, tan hyperbolicus. And then I have a minus g of t divided by v of t. So this is something which is nice to see, because we can then compare our numerical efforts with the analytical solution and just see if that agrees with what we get numerically. Now, when we have the velocity, we can then integrate and get the position y, because we know that that's equal to v of t. And that leads to, as we did last week, that leads to an equation for y of t minus y of t0, which we label as a y0. And this is going to be equal to the integral from t0, which we put equal to 0. That's just a convenient choice of dt prime multiplied with vt prime here. And that means that we need to plug in, so we get a y of t, which is equal to y0 plus, and then I have an integral from 0 to t of dt prime multiplied with this constant vt of tan hyperbolicus minus g, and then I have a time t prime divided by this quantity vt here. Now, this is an even nastier equation to find the paper and pencil solution to. So again, here you can actually use tables of integrals. And what you will find then is that your final solution, y of t, is going to be given by this y0 minus. And when you look up the table of integrals, you will find that this integral here can be rewritten in terms of the log of a cosine hyperbolicus. So this is definitely not something which you would get at a midterm or a final exam. But sometimes it's good actually to see that some of these equations can be solved analytically. Now, the thing which is interesting is now when we move to 2 dimensions. And you will then see that this is one of the first cases which cannot be solved analytically. And you will see quickly why that is the case. So let's move to 2 dimensions. So this is a new example. 2 dimension with a drag force, Fd, which is now, and now we have to be a little bit careful, and this is going to be given by this constant d. I'm going to have the vector, and then I need the absolute value of the velocity. This is actually the way this is expressed mathematically, because we now have a force in 2 dimensions. And we are going to choose a coordinate system as we discussed last week. So we choose a coordinate system. And we choose now a coordinate system, which is so that we have y, the positive y-axis, pointing upwards. So this is y, and we have the x-axis here. Then velocity is now going to be given by a vector which has v of x and v of y. And we will typically write v equal to v of x times the unit vector in the y direction plus v of y times the unit vector in the y direction. And similarly, we are now going to have a force which is going to depend on these quantities here. So we would have a force F of d, which is now going to be given by d. Sorry, we have a d here. And what I haven't defined now is whether this has a positive or negative sign, but it's going to depend on the velocity times the velocity, the absolute value of the velocity. And just to quickly remind you of that, so this v is going to be this v absolute value. That is the same as vx squared plus vy squared. When we then analyze the problem, and we want to solve this analytically now, we have to keep in mind that we're dealing with a two-dimensional problem. So that means that there's going to be an acceleration in the y direction, and there will be an acceleration in the x direction. So we would have a force now, the net force, which is given by the gravitational force plus this air resistance. And if we now write the force out, we have to be a little bit careful because we will have a force in the x direction and one in the y direction. So if we now look at the force in the x direction, that is definitely going to be given by, if we have this specific term, we would have a d times v of x multiplied with y, and then multiplied with the absolute value of v. So that would be the force in the x direction. Now, if we now look at the force in the y direction, so this will definitely then define the mass of the object times the acceleration in the x direction. And finally, we have the same equation for the y, a similar equation for the y direction. So we would have j multiplied with this v here, and that defines our m multiplied with a of y. So this is where we are now going to dissect the problem, and then we would like to repeat what we did before. But we have to be a little bit careful because we know that the a of x is going to have an equation of motion, a component in the x direction. So this is going to be given by this. And we know then that there is a new equation here, v of x, which is going to be given by dx dt. Similarly, I'm going to have a new equation for dvy and dt, and v of y is given by dy dt. So the complication now is that in the previous case, we had a second order differential equation, and we could split that in two coupled differential equations. Now, what happens when we move to 2 dimensions is that our second order differential equation now splits in 4 coupled first order differential equations. So if I were to do this in 3 dimensions, I would actually get 6 coupled differential equations. And you see quickly the complexity here. And this is something which we are going to study in more detail also when we look at the solar system. Because then if we solve the solar system in a Cartesian system with x, y, and z components, we are going to get a given number of coupled differential equations which depend on the dimensionality of the problem which we have. Any questions so far, guys? Does this sound okay? This is actually the kind of complication we get when we move into 2 dimensions. And you see easily that if you were to do this in 3 dimensions, you would just get 2 more equations to solve. So if we now take these equations which we have, we know that in the x direction, if we take this specific force which we have, so we would have this Fy, this specific force, this Fd, and I should actually put a d here, I forgot to do that. If we now look at the net force in the y direction, Fy net, that is going to contain the gravitational force minus mg, and then I'm going to have plus d multiplied with this v of y, and then I'm going to have a j, and then I'm going to have this absolute value of the force, of the velocity. So clearly then, my acceleration in the y direction, which we're going to call the net acceleration, is now simply going to be given by minus g plus this constant d divided by m times vy of j times v here. Sorry, I don't have the v, this quantity here. So I should take that one away because that's the force in the y direction. Okay, And then I would have a similar one in the x direction. Ax net is simply now going to be given by this quantity d divided by m times v of x, or v here. So let's now look at the differential equations which we have. So we are going to have a differential equation for the velocity in the x direction. That's the total velocity which we have. So we write a tot, or net velocity. And that is going to be given by this d divided by m times this vx of v. And at the same time, I'm going to have the same differential equation, the total one, velocity in the y direction, which is going to be given by dt, and that's going to be given by this d of m of v of y multiplied with v, and then minus g here. And now I want to integrate up here. But there's something you should pay a little bit attention to now. So if we write this out in more detail, so let's now write out these equations, and you will see quickly why these cannot be solved analytically. So this is going to be given by this d over m, and then I have a v of x, and now I have to put in the absolute value. So I have vx squared plus vy squared. And then I have my dvy total with a derivative respect to dt, which is now dm v of y with v of x squared plus v of y squared and minus g here. Now, one thing I said, is that this equation, it could be solved analytically in case you were to find a smart transformation. But if you look at the equation here, why can you not solve this equation analytically? Can you see any immediate argument for why you cannot do that? So this is actually something you would play around with in homework 3, where you're actually going to write a code, and then you can actually solve this without any problems. But why would it be difficult, or in this specific case, it's not possible if we insist on Cartesian coordinates, to find an analytical solution here? So any good arguments for why it will be difficult to find an analytical solution?
Can you not separate the x component? Like if you were trying to solve for dvx?
Fantastic. That is the answer. So the thing now which you see is that the vx component depends also on the vy component. So if you now look at the equations here, so let's single them out. So I obviously, if I had only vx here, I could actually have done this as I did in one dimension. But you see now that in the vx equation, there is actually a vy component. And then I have a vx component here. So this is a case where we cannot separate vx and vy. When you see something like that, that is a clear hint that you may not be able to find an analytical solution, because now we have to know the value of v of y when we solve the equation for v of x. So we cannot, the basic message here, we cannot separate the equations with respect to the unknown variables vx and vy. So this often leads to no analytical solution, or no easy route to an analytical solution. So let's just write this down here. So if you see a case like that, that means often that there may not be an analytical solution, or it may be difficult, or we may have to change to other coordinates, to other coordinate systems. Now we have insisted on the Cartesian system, to other coordinate systems. This is actually the case. You're going to have a similar set of equations when we are going to look at the Earth-Sun problem. And this is going to be homework number 5. So we are simply going to replace these falling objects with the Earth and the Sun interacting with the gravitational force. In that specific case, if we again insist on Cartesian coordinates, then we cannot separate the x and the y degrees of freedom in two distinct differential equations, but we will have what is normally called coupled differential equations. So these are coupled because we cannot separate the two unknown variables. So coupled diff equation. Numerically, there is no problem at all. Numerically, we would just integrate. We would have an initial guess for v of x and v of y, and we would just keep integrating up. Now, I mention this because when we come to the studies of the Earth-Sun system, if we make a smart transformation to either polar coordinates, if we are in 2 dimensions, or if we are in 3 dimensions, we make a transformation to spherical coordinates, this is a type of equations which could be solved. So I'm not saying that this is a case where you cannot find an analytical solution, but it's actually a case where you can see this as a kind of flag that maybe if I'm a little bit smarter, I change my coordinate system into another one, and perhaps in that case, I can find an analytical solution. But as it's written now, we cannot separate the variables because we have coupled differential equations. Now, let's see a case where we can actually do this, where we can integrate. And this is also part of the homework number 3. So in a certain sense, we're actually looking at the different exercises in homework number 3 as well. And the case which we are going to look at now is a case where we replace, and this is now example 2 here. In our case now, we are going to take this Fd to be given by a simpler force, which is going to be given by the velocity. So we're going to have m times a constant gamma, and then we multiply with just the velocity. So we don't have the velocity squared. As you will see now from the mathematics, this is a case which we can solve analytically. And this will allow you, when you're looking at some specific data, to figure out whether the air resistance follows a linear dependence on the velocity or whether it has a square dependence on the velocity. This is also very useful when you're going to solve this numerically, because you have analytical solutions you can compare a 2-dimensional or even a 3-dimensional case with. So let's go through the calculations here. And what we are going to have, in addition to that, we are going to have the gravitational force, which we are simply going to write as a minus m times g times the vector j. So we are looking at something which falls in the y direction, in the negative y direction. And the net force is again just going to be the sum of Fd, the air resistance, plus g here. And I'm going to put a minus sign in front here. This is just a convenience. You just have to pay a little bit attention to how you define the positive and the negative x and y axes. So again, the acceleration in the x direction is going to be given by dvx of dt. And if we now look at the expression we have for the force, we divide now with the mass, so we get obviously the acceleration then. And what we are going to get is minus gamma times v of x as a function of time. And this is going to be our a of x function of time here. So this expression here is actually something which depends directly on the velocity. And this quantity which you see is something which we can easily integrate up here. The next equation which we have is the equation for the acceleration in the y direction. So we have a dvy of dt, which is now going to be given by this minus gamma. We have divided away the mass. We have vy of t, and we have in addition the gravitational acceleration. And then the final 2 equations which we need to look at is a dx dt, and then we have a v of x, And finally, we have a dy dt, which is equal to v of y here. Now let's now do the analytical calculation, because this is a case which we can now integrate analytically. So what we have from the first equation is dv dx is equal to this one. And this is the famous differential equations. And I'm going to ask you what this gives us. So let's just set it up here. So we have a dvx dt is equal to minus gamma of v of x. And now we divide by v of x on both sides. So which now gives us dvx divided by v of x. And this is given by minus gamma of dt. We integrate up here. So we have then a dvx prime divided by vx prime. And we integrate from a initial velocity v0x up to a final velocity v of x. And this is going to be given by minus gamma integral from t0. And now we put again t0 equal to 0, which is very convenient. Now, this is something, this differential equation here is probably a differential equation which you have seen in many physics examples. And it has actually a name, this type of equations. Does anyone remember what kind of name we give to this type of equation? Because it has a solution which depends on a famous function here. Anyone remembers that? So there's a famous mathematical function which gives us v of x in terms of time. And some of you may have seen this mathematical function, it's a famous one, in connection with the decays. So if you look at things like beta decay of nuclei, this can often be modeled in terms of a simple function, which you have seen many occasions. And it gets from the decay, the physical decay, or like a beta decay, it actually has a name.
The exponential function?
Yes, and you typically call this the exponential decay. So you can see now that if you integrate up the function here, this gives you a logarithm. So you would typically now get the, if I integrate the left-hand side, I will get the log divided by vx v0x. And this is equal to minus gamma times t. And then I simply exponentiate this one, both sides. I take the exponential. So that gives me that v of x as a function of time is given by v0 of x multiplied with the exponential of minus gamma of t. And you will often see this called the exponential decay law. So that means that when we are studying this object which is falling, after some point, it comes at rest in the x direction. And that's simply due to this decaying function. And you will see this being called the exponential decay. So this is a case where we now, if you look at the equations here, which we had, there is no dependence on Vy. So if we go back to the two equations and compare that to the case when we had the velocity squared, you see now that in this case, we simply have V of x. There is no V of y dependence. And here we have V of y, and there's no V of x dependence. So we can actually now separate the x and the y degrees of freedom, and hopefully we can integrate up analytically. So that means that the V of x case can now be integrated analytically, and we can do the same thing with the position in the x direction. So we will now simply get that V of x is also equal to dx dt. And this is a quantity which we now would integrate up again. So we would get the integral from an initial position at time t equal to 0 to a final position. And this is going to be given by dx dt. No, sorry, not dx prime, but dt prime. No, sorry, we're just integrating from sorry, I'm multiplying away dt. This is me making a confusion now. like this. And this is going to be equal to the integral from t0, which we put to 0 for convenience. And this is going to contain dt prime. And then I have my vx, which depends on this time prime. And that means that when I integrate the right-hand side, I get x as a function of time minus my initial condition, x0. And this is equal now to the integral from 0 to t of dt prime, and then multiplied with v0x, and then e of minus gamma of t prime of dt prime, not dt prime here, but just the function here. And we know that the integral of the exponential simply just gives us a new exponential plus some constants. So when I reorder here, what I get now is that x of t is given by x0 plus this v0x divided by the constant gamma, and then I get 1 minus e to the minus gamma of t. And this is one of the functions which are going to play a little bit around with in homework number 3. So it's very useful to actually solve these equations analytically, because then we can compare our numerical calculations with that. And this is something which you will also find in Taylor's textbook in chapter or sections 2.1 to 2.3. He actually goes through, the author goes through the solution of the same type of equations. And it's actually very useful to look at that. So the next thing which we need to look at is the y component. And I'm going to give you the answer now. I'm going to set up quickly how we can reach the solution. So we have a minus gamma times v of y minus g. So this is the expression which we had for the acceleration in the y direction. Now we can isolate these equations. So what I'm going to do now is to multiply with gamma and on both sides, or divide by gamma. So I can simply rewrite this equation in terms of a dvy. So I take the left-hand side, I multiply with dt, and I divide out the other terms. And then I get a v of y plus this g divided by this constant gamma. And this is equal to minus gamma times dt. So the thing I did was simply to multiply with dt on both sides. And then I divide with gamma vy minus g and divide again by with this parameter gamma. And then I can rewrite the equation like this. Now, when I have done this, I can then integrate. And you will see that the function which we end up integrating is going to give us a logarithm again. So what we get then, when we integrate up, we are going to integrate from some initial velocity, v0, in the y direction, up to a final velocity. And then we are going to have the integral of a velocity. We are separating the variables. So we're going to have a v of y plus this g divided by this gamma. And this is going to be equal to minus gamma from time t0, which we put to 0, to t of dt prime. And this one is simply going to be minus gamma of t. Now, the function you get when you integrate up with respect to the velocities is again going to be a logarithm. So what you have here is simply going to be given by ln, and then I have a v of y plus g divided by this constant gamma. And this is now divided by v0y plus this g divided by gamma. And this is equal to minus gamma times t. And then I take the I exponentiate both sides. And what you get then when we exponentiate both sides is that v of y as a function of t, I'm introducing that one again, is going to be equal to minus g divided by gamma plus e of minus gamma of t. And this is then multiplied with, and put multiplication sign, with v0 of y plus g divided by gamma here. So this is going to be my answer when I'm setting up the equations for the velocity in the y direction. And then we can set up the same thing when we are now looking at the position in the y direction. So we know that Vy of t is going to be equal to dy dt. And then when we repeat integration, so I just want to give you the final answer here, we are going to get something which looks like y of t is equal to the initial velocity, the initial position, minus g times t divided by gamma, plus, and then we're going to have a new term, v0 in the y direction, plus g divided by this constant gamma, and multiplied with 1 minus e of minus gamma of t, and multiplied again with 1 over gamma here. So that's going to be the final expression. So it's not a very exciting exercise, but it's more meant to show you how we can actually find an analytical solution. And this is extremely valuable when we're going to analyze the results and when we're going to compare our codes or falling objects in 1 and 2 dimensions. And in this specific case, we have an analytical solution. I just went a little bit over time, which is always easy when you're teaching via Zoom. I'm going to stop the recording here. And then